Great, thank you very much. Thank you for having me. Excited to be part of this this workshop. And actually, Daryl, there will be, hopefully circle back with one slide at the end to some of the issues that you were raising at the end of your talk. I think there are kind of two themes that were interesting in what I heard you talk about. One being the perturbation of the system as you're measuring, and that's that's something that we'll see actually as we go through. And then the other one is just how rich networking is as a domain within which to advance the state of the art at the intersection of data science and queuing. So I'll try to come back to that theme at the end. Hopefully there's a nice linkage between the two talks. So this is joint work with Jose Blanchett, Peter Glynn, obviously my colleagues at Stanford. Peter gave a talk last night, as well as Mohammed Rasuli, who is a postdoc with us at Stanford, and Linjia Wu, who is a PhD student at Stanford, currently working with Jose and Peter and myself. So let me, oh, sorry, I'm on my iPad here. So, what's the motivation for this work? I think the main thing I want people to have in mind, kind of what's interesting about this work to me, is that if you're any one of these platforms, and really there's many more, a very common problem that these digital platforms come across today is that you have two algorithms for the same task that you want to compare. So an example might be, and I think a prototypical example actually that I want you to keep in mind for the whole talk might be something like a matching algorithm at Lyft or Uber, at a ride-sharing platform. So, what is the state of the system as seen by the matching algorithm? It's the current set of available drivers and potentially the current and maybe recent outstanding ride requests that want to match to drivers. So, each of these algorithms that you're comparing has the basic feature that once you make matches, you've changed the state of the system. You've changed what available drivers there are. You've changed what ride requests there are. And this kind of idea that the algorithms change the state of the system, unfortunately, does not play well with classical randomized experimentation. So I think a very basic question in experimental design is, how do you design experiments and estimators to compare two algorithms that change the state of a system? Okay, so that's sort of the core question that motivated some of this work. And so I've divided the talk into two parts. One of them is going to talk to you about, kind of a relatively theoretical approach that we took that just kind of grounds some interesting ideas, I think. And then the second half of the talk is similar in spirit to the way Daryl presented, which is to talk more about sort of like some of the issues and challenges and questions that this kind of work raises. Okay, so let me start by describing what perhaps a naive approach that is actually commonly used would look like, which is, and actually, sorry, backing up, I should be more explicit. What does it mean to evaluate the performance of these two algorithms? The typical question that these platforms are asking is, if I have algorithm A and algorithm B, and I run the entire system around A, or run the entire system around B, what's the difference in the steady state performance of these two algorithms that I can expect? And so, the performance we're going to measure through some notion of reward as a standard in Markov chains. For example, in the context of a matching algorithm, you might be interested in the steady state rate of rides that are delivered in the system if you use algorithm A versus algorithm B. So given that the algorithms are changing the state of the system, a very natural way that you could try to compare the two is to, at each decision epoch, randomly flip a coin and run either A or B. Okay. So, for example, in a ride-sharing system, every decision epoch might be when a rider arrives. You might choose, well, which matching algorithm am I going to run on this particular ride request, A or B? Okay. So that actually is, that particular type of design is what's called rider-side randomization in a ride-sharing platform. You can ask, well, why is that not a good idea? So the typical problem is that this creates what's called a carryover effect, and what I'll also refer to as temporal interference. When I apply algorithm A, I change the state of the system, but that becomes the initial state as seen by algorithm B. Okay, So experimentation by dividing time into individual time units actually creates interference between the experimental units, because when I run algorithm A, I change the state as seen by algorithm B. A little less obvious form of this example, but nevertheless very important in practice, would be something like the following. Let's suppose you divide time into, let's say, 2-hour blocks, and you run algorithm A during the first 2-hour block, then algorithm B during the second 2-hour block. But if algorithm A is an algorithm that aggressively grabs drivers, then it will take driver supply away from algorithm B, so that algorithm B will systematically see a, relatively speaking, resource-starved environment whenever it is run. And so, in this situation, what's happening is that that change of state from one algorithm to another is actually creating what statisticians would call interference between the experimental units. And it's kind of a well-known fact that when you have interference between experimental units, then the risk is that you have bias in your estimation of the treatment effect, as I've defined it here. More practically speaking, in the example that I just gave you, if algorithm A systematically grabs a lot of driver supply and therefore leaves algorithm B in a biased state of the system relative to what its steady state would have looked like without the experiment, then we will underestimate the performance of algorithm B, and therefore we will overestimate that gap between A and B. Okay, so so this is kind of a basic problem, and if you take that naive design that I described and you think about running it with longer time intervals, you get some picture like the following, where time is divided into fixed length, non-overlapping intervals. In each successive interval, we assign one of A or B. We could even alternate the two if we wanted to, deterministically. And we compute the sample average of performance within each of these intervals. And we take the sample average performance of algorithm A, the sample average performance of algorithm B, take the difference, and call that our treatment effect estimate. So there is, with this type of design, there's a lot that we could say about how these designs are used in practice. Switchback designs are actually quite old. The first paper on switchback designs specifically was a paper by Oman and Seiden from the 80s that talks about them in the context of livestock experiments. And one of the kind of important things to think about here is that if your experimental unit is this block of time, then one way you could eliminate that temporal interference effect, the carryover effect, is by progressively lengthening the blocks A and B, because if you lengthen those blocks, then the dependence on the initial conditions for both A and B becomes weaker. The problem with lengthening the blocks is that if you're treating each of the blocks as your experimental units, then any analysis that treats those as the units also is decreasing the sample size effectively within the same amount of time. So there's a lot of reasons why sort of thinking through analysis of these experiments, the bias, the variance, and how to deal with behavior of the process within each interval is actually a somewhat challenging process. And I think this remains actually a really interesting area of investigation, just to develop novel structural methods for analysis of switchback designs in queuing systems. What I'm going to do is I'm actually going to cast that entire problem slightly differently. And talk to you about a nonparametric Markov chain viewpoint on that problem. And I'm hoping that you'll find it interesting. Primarily, I think it's useful as a way to frame what the actual experimental design problem is in that context, and to talk about it through that perspective. And what that's going to then let me do is talk to you about some challenges and opportunities. And I have these 4 bullets under here that we'll come back to towards the end of the talk. Okay, I'm hoping to have left plenty of time for discussion and questions, and I'll try to keep an eye on the Q&A as the questions arise. Okay. So let me, like I said, I'll spend the first part of what I have to say kind of talking about this Markov chain viewpoint. And what do I mean by Markov chain viewpoint? So here's kind of the key idea that we took in this work that we did. The basic idea was to realize that if I fix one of the algorithms, if I fix A or I fix B, then effectively what I'm doing is I'm inducing a Markov chain on the system. And so one way that I can think about the problem that I'm interested in is that I have 2 different Markov chains that operate on the same state space. And I'm interested in estimating the difference in steady state reward between these two Markov chains. Okay. So that's kind of the key idea. It's a simple idea actually, but it turns out to be quite powerful as a way to just frame the problem. And importantly, I think for this community, it's a formulation that admits a lot of nice structure and turns out to have some nice connections to other more classical lines of work within stochastic analysis. So, so that's kind of what I'll spend my time telling you about first. Just a fair warning that what I'm going to tell you about is going to look very far away from the more practically grounded introduction that I gave you. And frankly, I would view that gap, that disconnect, actually as part of the research challenge in this area. And I'll try to come back to that and comment on it a little bit more towards the second half of the talk. But for now, let me ask you to kind of suspend your practical disbelief and just focus on kind of what's the interesting theoretical problem that we're talking about here. So we have, setting up the formalism of the model. We have discrete time, n is 0, 1, 2. We have finite state space to keep things simple. So we have x and y denoting states. And now I have two algorithms. So I'm going to refer to the algorithms as actions, denoted by 1 or 2. But really, like I said, these actions are just indexing two different chains. And so what I have are these two unknown irreducible transition matrices, P of L, indexed by 1 or 2. So each one of those is a Markov chain on the state space or just a transition matrix on the state space. Okay. Because they're irreducible, it's finite state space. Each of these two transition matrices has an invariant distribution that I'll denote by pi, and I'll think of it as a row vector. Okay. Again, those invariant distributions are indexed by 1 or 2 for the two corresponding Markov chains. Now I'll assume that if I'm in state X, I transition to state Y using chain L, that I obtain some reward that's drawn from a distribution that depends on L, X, and Y with a finite mean invariance. And a key quantity for us is going to be this expected reward that's earned when I'm in state X and I play chain L, which is just the expectation of this random variable R if you play chain L in state X. And in particular, that expectation is over both the randomness in the reward and the randomness in the next state. Okay, and we'll think of that R as a column vector, as is fairly standard. So pi is a row vector, R is a column vector for each L and for each LX respectively. Okay, so at time n, I have some state capital Xn. I take an action an, which is to choose one of the two chains. I obtain a reward Rn. Okay, that's like the basic specification of the problem. So now the question is, well, how do I formulate the treatment effect, that thing that I was interested in measuring, what a statistician or econometrician would call the estimand of interest? So the estimation problem is that we are interested in estimating the steady state reward difference between these two Markov chains. Remember, pi is a row vector, R is a column vector, so this is just the dot product between steady state, this is the dot product between the steady state distribution of chain 2 and the reward that's earned by chain when I play chain 2. And I think I misspoke earlier, by the way. I think I referred to RLX as a column vector. RL is a column vector. RLX is obviously just the scalar quantity here. Okay, so this is the steady state reward that I earn if I play chain 2. So steady state reward if I play chain 1. And I take the difference of those two quantities. That's my treatment effect of interest. Okay. So, the central problem, what in the causal inference language would be called the fundamental problem of causal inference here, is that I only have one system. And on that one system, I can only run one chain at a time. So unless I run, chain 2 for essentially an indefinite amount of time, and then chain 1 for an indefinite amount of time, I can't obtain an unbiased estimate of this quantity. I'll have some carryover effect at the moment that I switch between the two, at any moment that I switch between the two. And so, one of our questions here then was, well, let's just attack this from first principles as a problem of trying to estimate this quantity when the fundamental constraint I have is that I only have one system. And so if you look at the problem that way, then what do you get to choose? Well, what you get to choose is, and I'll say this in reverse order, what I get to choose is, at every time step, which of the two chains do I want to run? So that's 1 or 2. And given the data that I've collected up to time n, what estimate do I form of this quantity alpha? Okay, so these are interconnected with each other. The estimator depends on the data that I've collected. It's adapted to the history. The data that I collect depends on the design. Okay, we allow the design to be randomized. So these are just these are adapted quantities, right? So this is kind of the estimation problem and the design problem that I face. Okay. Now it's not surprising that if you're jointly allowed to choose the estimator and the design, this can become a very complicated problem in a hurry. What we did is we focused on a situation where we use a pretty natural approach to estimation, which is maximum likelihood estimation, and then ask, well, if we use MLE, what is the best design that we can come up with for this problem? Okay. So I hope kind of what you're taking away from what I've said so far is that I think one of the things I want to do is I want to strip away all the practical complexities of this problem and ask at some more fundamental level, what is the estimation and design problem that's being tackled here? And I think that, while what I'm about to tell you is totally impractical for reasons we'll talk about in a second, I think it is conceptually valuable because it shows us sort of, what is the fundamental limit of what we're trying to accomplish here. And if you want to get away from these limits, you either need to change the question that you're asking of the data, all right? Or you need to sort of take advantage of problem structure in ways that this fully non-parametric approach does not, all right? So I think it's good to think of this as kind of almost a benchmark setting within which to think of this problem. Some definitions here that look more complicated than they really are. Gamma denotes the number of times I've played chain L in the first n steps. So it's just a counting process. Rn is the sample average estimate of the reward, of the expected reward. So here what I do is I take the rewards that I've actually earned and I take the average of those over the time horizon up to time n. And finally, this P here is just an empirical frequency of the fraction of times that I played chain L and was in state X that I transitioned to state Y. Okay, so Pn is a transition matrix. Once I have sufficiently many, and once I have non-zero observations in every one of the states, and what I kind of want to get across here is that these are essentially the non-parametric maximum likelihood estimates of these quantities. And therefore, using sort of equivariance, what we end up with is that the pi n, which is the invariant distribution of Pn, once it exists, is the non-parametric maximum likelihood estimate of the stationary distribution. So if I plug in, pi n and Rn as estimated from the data, then this is a non-parametric maximum likelihood estimator for the treatment effect. It uses the two non-parametric MLEs for the stationary distributions, the non-parametric MLE for the reward functional, for the expected reward functional. Okay. All right. So here's a approach to developing an estimator if I had a policy. So now what we're going to ask is, well, okay, if that's the estimation approach that I'm using, then what policies do well? And it's not surprising why we would use MLE here, because we're expecting that sort of the MLE has good sort of large sample properties in terms of efficiency, and so this kind of focused our attention then on how best to design the experiment so that we can achieve sample efficient estimation with the MLE. Okay. So there's one regularity condition I need on the space of policies that we consider, which is called time average regularity. And time average regularity is a pretty benign condition. It basically says that if we look at the count of times that we played chain L in state X, and we divide by n, which means we look at the frequency, that those frequency have well-defined limits in probability, right? Now those limits are allowed to be potentially random, okay? But the key thing is that there is some limiting law of a random variable with convergence and probability to that random variable. For our theory, we require that random variable to be greater than 0 for every chain L in state X almost surely, okay? We call this gamma the policy limit. And I'd say this is a pretty benign requirement, mainly because to break this requirement, you need something which on exponentially longer exponentially increasing timescales is flipping between the two chains, for example. And so I think it's pretty reasonable to expect for most reasonable policies that you could think of, and that you would end up having these well-defined policy limits for those kinds of algorithms. Okay. All right. So let's say we restrict attention to time average regular policies. So kind of a key theorem that drives our results is the central limit theorem for any time average regular design with strictly positive policy limits. Now I want to note that what's happening in this central limit theorem is that we are using the true values of the primitives, the true transition matrices, the true rewards, and therefore the true stationary distributions. And we're expressing the scaled asymptotic variance of the treatment effect estimator that we obtain under this design A, or this policy for choosing the chains A. We're expressing the scaled asymptotic variance of that estimator in terms of these primitives, okay? So in particular, what are the primitives that enter? So the gammas here are the policy limits that I mentioned earlier. So these are the limiting frequency of time that I play chain 1 and 2 respectively in state X. The summation here is over the state space. The G's are IID normal random variables. And we have this scaling constant in front, which is a sum of the stationary distribution entries for each chain times this sigma, which is like a standard deviation. And so how do we interpret the sigma? Okay. The sigma, easier to think of sigma squared. Sigma squared is the variance of one-step reward plus G tilde for the next, for that chain L that we played in the next state. Now, what is G tilde? G tilde is the solution to Poisson's equation, okay? So Poisson's equation kind of is an incredibly useful tool in looking at the behavior of this the variance behavior of these time averages, which is exactly what we need here. This is the solution to Poisson's equation. This is what's called the fundamental matrix that appears here. Pi is a matrix where each row is the stationary distribution, and R is, remember, that column vector of expected rewards in each state X, okay, for chain L. So we obtained the solution to Poisson's equation and look at the variance then of this random variable, okay? Again, the randomness here is in the reward random variable and also in the next state, given that I started in chain X and I played chain L, okay? So that's what gives rise to this variance, and in turn, that's the sigma that we put here. So, how does this end up playing a useful role? In our particular case, one thing that's very valuable about Poisson's equation is it allows us to change from statements about perturbation of the invariant distribution, in particular, differences between the nonparametric MLE estimate of the invariant distribution and the truth, to convert from that to differences between the nonparametric MLE estimate of the transition matrix and the truth. Okay, so that's what I want to kind of just talk about briefly here, where what we have is this difference between the nonparametric MLE estimate of the reward and the true steady state reward of chain L. And if you write that out, what you see is that one of the quantities that you need is to look at the difference in steady state distributions between this nonparametric MLE estimate of the steady state distribution and the truth. You need that difference inner product with the reward vector. What we do is we use Poisson's equation to convert that into a difference between the transition matrices, with the G tilde that appears in Poisson's equation now being the quantity on the right-hand side. And this is useful because we can then use martingale arguments to handle adaptive sampling and the impact of that on the maximum likelihood estimate of the transition matrix, okay? So this is kind of a really nice combination of Poisson's equation with martingale methods for analysis of Markov chains to be able to obtain the central limit statement that we have here. Now, once you have that central limit theorem, there's actually a lot of nice things that happen. Perhaps the most important thing is it gives a really convenient convex characterization of an optimal sampling policy. So we define the set K, which is a convex compact set of all kappa Lx that obey this system of three equations. Now I want you to think of kappa Lx as a probability distribution over, chain choice 1 or 2, that's L, and state X, okay? And in particular, I want you to think of this as kind of a limiting frequency with which we play chain L in state X. So given that interpretation, the sum of the kappas has to be 1, they have to be non-negative, that makes sense. And what's happening here is just flow conservation, okay? So if I'm in chain X and I play chain L, sorry, I'm in state X and I play chain L, this is the probability that I transition to state Y, right? And this is the cumulative frequency with which I'm in state Y because I play chain 1 or 2 in state Y. So this is the typical kind of flow conservation requirement that we have, except now it's broken apart across chains 1 and 2. And our key lemma is, this is not very hard to show, it follows from all the conservation laws that I just described, that the law of any time average regular policy limit, which is, again, the policy limit is the frequency with which I play chain L in state X, must be a probability measure over the set kappa, okay? So that's very useful because then if I want to obtain an optimal policy design, one way I can characterize that is by saying, well, let's minimize the variance of that limit random variable that we obtain in this CLT. So the variance of this random variable, remembering that these G's are all independent normal 0, 1 random variables, the limiting, the variance of that limit random variable is just this quantity here, okay? And so, if I look at this quantity and I optimize this quantity with respect to the kappas, the script K is a convex compact set. The kappas all appear in the denominator. So this is a strictly convex objective function, has a unique solution that I can solve. And that solution is, let's say, denoted kappa star. If I run this stationary Markovian design, which means that in state X, play chain L with this probability, then I obtain an algorithm for adaptively sampling the two chains, for sampling the two chains that exactly yields these policy limits kappa star, okay? So this certainly then, what we've established is that this is a policy that obtains scaled asymptotic variance that's optimal. Perhaps, slightly more interesting is that it's not only a policy that achieves that, but it's actually optimal across all time average regular policies. And basically to establish that, we can just use Jensen's inequality on the asymptotic variance of this scaled estimator, okay? So, what we obtain with P star is a policy that's stationary and Markovian that samples the chains according to, the proportions that I gave you on the previous slide. And in fact, then yields optimal asymptotic variance. One thing I guess I should point out that I didn't say that's clear is that if we have any policy like this that is sampling with frequency that's greater than 0 in every state, and we're using non-parametric maximum likelihood estimation, we get consistency of our estimator for free. So as long as we're collecting enough samples, which is what's happening here, then consistency arises for free because that non-parametric maximum likelihood estimate will converge to the truth asymptotically. So that's kind of an important point to make because consistency is what does away with the carryover effect that we're worried about. So this is a way in which using maximum likelihood estimation asymptotically at least does not leave any bias. Whereas I want you to note that if you're using any sort of a switchback design with a fixed interval length, even asymptotically, you'll have a constant bias away from the truth, okay? So all these time average regular policies are consistent, And kind of what we've obtained here is what would be the optimal policy, right? One obvious issue with what I gave you here, besides sort of many computational issues that I'll get to in a second, is that the policy here is something which is computed using knowledge of the truth. And of course, if I knew the truth, I wouldn't be running any sort of an experiment in the first place. So, one of the things, I'll come back to this slide in a second, but one of the things I just want to say is that we also propose in the paper an optimal online design that yields the same asymptotically optimal policy limits, but does so in an online adaptive fashion by using what's called forced exploration, which will be familiar to anyone who's worked on multi-armed bandits. The idea is essentially that I force myself to sample the chains, with some positive probability over time. And what that's doing is it's making sure that I'm collecting enough samples of each chain that now, my nonparametric MLE estimates will converge quickly enough that I actually do converge to the correct kappa, the correct frequencies of play for the two chains. So this idea of forced exploration here makes it quite straightforward to convert the offline optimal policy on the previous slide into an online optimal policy that I'm giving you on this slide. Okay. One last comment that I want to make qualitatively just about the structure of the solution is that, one of the things that this analysis revealed is that kind of you benefit in variance by taking advantage of what's called cooperative exploration. Okay, so what is cooperative exploration? The idea is that I can actually use each chain to explore the other. And this is kind of an extreme example of that phenomenon that's depicted on this slide, where I have S states and I have two Markov chains. Those are my two different policies. One of them moves deterministically counterclockwise to the right. The other one moves deterministically counterclockwise to the left. Okay. One of them moves deterministically counterclockwise. One moves deterministically clockwise. Okay, that's a better way to say it. And what I want you to imagine here is that we earn a policy-dependent reward in state one and zero reward elsewhere. So in that case, if you estimate using the red or blue chain alone, that has asymptotic variance that's going to be order of S, the number of states, higher than using both together. Why? Because if I use either chain alone, I have to circle all the way around before getting one observation of the reward. So that's going to take me, S time steps to make that happen. So I'm only getting one observation every S time steps. Whereas if I use both chains together, I can, bounce back and forth. So let's say I use chain one, I get an observation here. Then I switch over and I use the red chain, I get an observation here. I switch over and again, use the blue chain. So I only need to bounce back and forth between state S and 2 in order to collect observations of each chain, all right? And that phenomenon is generic to the setup of the problem. And that's an example of what I mean, where this kind of fundamental viewpoint on the problem provides some conceptual clarity about exactly what the ways are that adaptive experimental design in this setting can actually benefit you, can provide some value to using one of your algorithms to actually learn about the other as you go. Okay, so this is kind of like, what are the main takeaways from this way of thinking? I think one of the key points I want to highlight here is just the modeling viewpoint of using two Markov chains to think about these two competing algorithms. And obviously in a queuing system, what that means is we'd be thinking about the same queuing system under two different policies that we're using to run those queuing systems. So, back to Daryl's talk, imagine that I have two different network algorithms and I want to compare those two network algorithms. So those would be the two induced Markov chains, A and B, on the same underlying system. And what this, talk is really getting at up to this point is that there are some fundamental limits in how well we could do in efficiently sampling there that are kind of coming from the underlying structure of those two Markov chains and our ability to adaptively switch from one chain to the other, okay? So that kind of adaptive ability to switch from one chain to the other is what's being encoded in this script K set here. And that's kind of where the structural insight comes from, that I can use one chain to help me with the other. That's from the structure of that set script K. that's kind of what shows up in the optimal solution, for example, in this simple example here. Okay. So, that's kind of that non-parametric maximum likelihood viewpoint on estimation. And now what I want to do is I want to step back a little bit, and I want to talk about some of the challenges and opportunities that arise in reflection on the work that we did there. Well, the first one is, it's kind of obvious that, this is clearly intractable in general. The optimization problem that I showed you for that kind of design is something which scales with the size of the state space. And, so there's a basic problem here, which is that the state space of real world queuing systems is in principle very large. So what are approaches that you could take to computational complexity? And I want to say that, I think this is a fairly big topic to think about because there are two directions you could go with it. One of them is to think about ways in which you could simplify the structure of that optimization problem, perhaps by thinking about more structured policies that you optimize over. Another way is really just to take a different perspective on the space of designs that you want to consider, which, that's effectively what we do here. So one way you could think about what we do here is that we're changing the design and estimation together to arrive at something simpler. So this is what we call regenerative experimentation. The idea is that you fix one state, the regeneration state, and then only change chains at visits to that regenerative state, okay? And then estimate your performance by using sample averages, as in the standard switchback design I showed you at the beginning of the talk. So as an example, let's suppose that, these are my regeneration periods for each of these chains. I have switching points at these, boundaries between the boxes. So what do? If I just stack these blue boxes and the red boxes onto each other, then I can use sample average estimation here. And kind of it's very well known that if I'm stacking up these blue boxes at the regeneration points, then long run, the sample average here does indeed converge without bias to the long run average reward of chain 1 and respectively for chain 2, okay? So this is kind of a way to get the simplicity of a switchback design, but to do so in a way that does not introduce any bias from the carryover effect, okay? Because we're always only changing state at these regeneration points. So, you could similarly leverage a CLT to solve for the optimal regenerative design. And kind of the main cost here is that because you only have 1 degree of freedom, which is the probability of switching at that regeneration state, the performance that you obtain can be unboundedly worse than what you obtain with that non-parametric maximum likelihood approach, where we allow ourselves to change the chain in any given state of the system. And there's a lot you can do with that. You could start to group states together, where you might allow yourself to make switches and so on, so using other techniques of state aggregation to manage complexity. Okay, but I think this is kind of like one way to think about complexity. I think there's a lot more to it, where you could really focus just on the computational side of this problem and think about ways to make solving for the optimal design and implementing the optimal design computationally more tractable. I think a reasonable transition there is then, well, one approach that we historically take in applied probability to reduce complexity is to use modeling, mathematical modeling. And I say, just to be explicit, I think in queuing, we really take modeling for granted. I mean, the foundations of the field involve modeling. I think this is sort of, it's a branch of stochastic analysis that prides itself on modeling at its core. But I want to stress that is not the norm in causal inference for systems with interference of the sort that I described today, right? So, how would the causal inference literature approach interference in experimental design? So I'll say this in a few bullets just in the interest of time. It's a deeper topic, certainly, so I'm giving a little bit of a caricatured viewpoint, but hopefully enough to get the point across. The idea is that in a causal inferential viewpoint, you would say, let's take the ride sharing example where you have riders and drivers. And let's suppose that what we want to do is we want to randomize the choice of the matching algorithm every time a ride request arrives. So that'd be, again, what I called rider side randomization, okay? So, what the causal inference literature would say is, okay, yeah, we accept that, whether I assign a given rider to algorithm A or B, that has an impact on the state of the system as seen by future riders. And therefore, the treatment assignment that I make to this rider impacts the outcomes that I might see for a future rider, okay? So the outcome that you observe on a rider is a function of the treatment assignment of that rider and all other riders that interfered with them. So that's called their potential outcome mapping. It maps the treatment assignments of all these riders into what outcome we would see on that particular rider, okay? Now, a problem is, of course, in general, that mapping is going to be extremely high dimensional. It'll explode in complexity as time goes on. Because as time goes on, I'll have more riders, which means that a subsequent rider's potential outcomes depend on the assignments of all the riders that came before them, okay? So what's done in the causal inference literature is to postulate a lower dimensional representation of this impact of other riders' treatment assignment on the potential outcome of a given rider, okay, or a given unit. That's called an exposure model. And then the goal is to estimate treatment effects by estimating the parameters of this exposure model, okay? This has a long history, really nice paper by Aronow and Sami in 2013 on this idea in network experiments. Yavor Bojinov, Jinglong Zhao, and David Simke-Levy have a recent paper on the specific application of this idea in switchback experiments. And there's a number of other papers on marketplace experiments and many others as well. So this is kind of a very standard approach for dealing with causal inferential estimation in settings with interference of the sort that I've described to you. I think it's important to understand, though, that in queuing systems, appropriate exposure models can be very hard to construct because of that point that I made, that interference is growing exponentially in time. And if you completely ignore any structure of the system, you're left with, really, I think, quite a lot of difficulty formulating a low dimensional exposure model that's believable. So this is something I've been quite interested in. I've been working actively on recently, where kind of the idea is to combine the best of model-based experiment design and estimation, which involves, I would say, more structured stochastic modeling, of queuing models, with the robustness that you obtain by using exposure models. So the benefits of exposure models, provided provided they don't make too many underlying assumptions about the system, the benefits are that they have a certain robustness to them. They're not assuming a lot about the behavior of the system. Of course, the benefits of queuing models are that we obtain a lot of tractability often by actually sort of postulating something about the structure of the queuing model we're working with. And so I think there is a lot of room here to combine sort of ideas from each discipline to actually obtain richer designs and estimators for practical use. Okay, one other thing I want to comment on here is that, in terms of the role of modeling, we've developed a similar approach to our non-parametric maximum likelihood results in a setting where you instead use a parametric maximum likelihood approach, which is very natural for queuing systems. So for example, in queuing control problems, you can imagine parameters that determine arrivals and service rates or service policy, and then compare two different queuing control algorithms where parametrically the lack of knowledge that you have is what's the impact of that algorithm on these different arrival and service characteristics. The benefits of a parametric viewpoint should be obvious here, which is that you have then the possibility of learning across states in a way that the non-parametric maximum likelihood approach does not admit, which can in principle yield a significant improvement in statistical efficiency. Potentially can also yield an improvement in computational efficiency if you're able to leverage that parametrization to simplify the computation of this optimal experimental design. So this is work that Linjia Wu, the PhD student in particular that I mentioned at the beginning, she's been leading. Another kind of thing that I want to draw your attention to here is that as I was commenting on at the beginning of the talk, there's a lot of different approaches that are used from an experimental standpoint to deal with interference. I talked to you about switchback designs. There's also what are called cluster randomized designs, which is where I divide my system into many subsystems. The most obvious example being different cities in a ride-sharing system. If those systems are essentially non-overlapping in their queuing dynamics, then I can randomize individual cities to treatment or control. And now my sample size is the number of cities I have. I can have what are called crossover designs, which are combinations of switchback and cluster randomized designs, where I randomize at the cluster level, and then within each cluster, I switch back and forth between the two different policies. So we have all these different kinds of designs available to us. In more recent work with Hannah Lee, who's a PhD student on the job market this year, Gabriel Weintraub, a professor at Stanford GSB, and Ines Eliskovic, who's a data scientist at Airbnb, we've developed the idea of what's called two-sided randomization, where you could randomize, for example, both riders and drivers simultaneously, and then develop estimation techniques for that randomization that try to control bias in estimation. And there's many ideas for using these, combining these, and developing associated estimators. And there's this big overarching elephant in the room, which is that there's very little guidance on what you should measure about your system that would suggest one or the other of these design and estimation approaches is preferable. So I think we still lack kind of a user's manual for a data scientist working in one of these systems that says, for your problem, you're better off using this design instead of that one. So I think that's kind of an interesting space of problems to think about. And finally, I just want to conclude by noting that, obviously, as many industries have digitized experimentation, the space of application of such techniques has rapidly expanded. Daryl talked to us extensively about communication networks becoming software-enabled, software-defined in a way that enables rapid experimentation, adaptivity, and control. And the same is true of logistics and supply chain networks. If you think about not only Amazon, but even more decentralized logistics and trucking delivery networks, there's all kinds of space for interesting experimentation there. Call centers, which have been an important application area for the queuing community, they've similarly undergone significant digital transformation that enables this type of A/B testing and experimentation. So the space of applications where novel and I'd say finely tuned experimental designs can be applied has really rapidly expanded. One thing I just want to mention, this is the slide that goes back to what Daryl was talking about, is that in a recent collaboration with Netflix, with Bruce Spang, who's a PhD student at Stanford, Nick McEwen, who's a professor at Stanford, and T1 Wang, who's actually a former student of ours from 10 years ago, who's now director at Netflix. What we did is we kind of worked on this idea that when new network algorithms are being A/B tested, they can create interference because the same underlying communication network is being shared. It's really just a version of the problem that Daryl defined, with perturbation, but at larger scale, where every time I'm running these two algorithms, if I run them alongside each other, so a standard Netflix approach to experimentation is to randomize some sessions to use algorithm A and other sessions to use algorithm B. Well, if they're doing that on the same network, then I don't really get a clean reading of what would have happened if all sessions had used A or all sessions had used B, because they're interfering with each other in the same congested network, okay? So we actually recently implemented switchback designs in the Netflix setting to compare against naive A/B testing where sessions are randomized. And what we found is that the interference could be so significant that it actually flips the sign of the treatment effect. So just to give you a little bit of a window into that, because I think it connects well with what Daryl was saying earlier, let's suppose that we have some intervention that actually reduces congestion if everybody uses it, okay? It should not be surprising that I can implement interventions like that nevertheless interact badly with an existing protocol that's already in use. Let's say that's the control protocol. In that environment, what'll happen is if I run the new algorithm alongside the control protocol, I may actually see congestion go up for everybody because of this bad interaction. But if I can switch everyone over to the new algorithm, then in fact, I see congestion levels go down. And that's exactly what we saw in the kinds of experiments that we ran. This is very recent work that's been conditionally accepted to IMC this year, and hopefully the paper will be up publicly soon once it's finished through the shepherding process. There's also lots of really cool things to do here. Challenges including combining network partitioning, which is the equivalent of that cluster randomization that I described, with various forms of temporally adaptive experimental design that I think connects up with some of the stuff that Daryl was describing earlier. Okay. I want to wrap up here. I have 2 slides on related work that I won't go into detail. I'll just quickly mention the bullets just in the interest of time, and then I'll wrap up. So, first is to mention crossover and switchback designs that have a long history in the clinical trials literature, especially. Here, I just want to flag this recent paper by Bojinov et al. That I mentioned during the talk, which is a very sort of it's the causal inference approach to thinking about switchback design. So I think it is worth looking at as a counterpoint to some of the stuff that I talked about here today. There's a great deal of work on mitigating interference in network experiments, which has a connection with what I'm talking about here. If you think about the network as being defined by interactions between units in a queuing system. So again, like I said, if a customer comes in, then that customer's, the algorithm that customer has applied to them will impact other customers that arrive subsequently. So if you think about this network of interference defined between customers, there's some interconnection between the kind of work I'm talking about here and this work on network interference. And then, there's sort of also quite a bit of recent work on mitigating marketplace interference, and including many of the works that I talked about during the talk. Separately, I just want to note that there's some really interesting connections to estimation within Markov chains and MDPs and reinforcement learning. One of the cool things about our work is that it's effectively an MDP with a minimum variance objective. That's generally intractable, but just the special structure of our setup and the particular estimand of interest makes it a convex problem. So that's nice to find. This computational intractability here is what I mean is you can't even get any structural characterization of the optimal policy in the way that we're able to. Also connections to reinforcement learning that I won't say as much about here. So just to wrap up, I think what I'm hoping to convey to this audience is that the digitization of online platforms and more importantly, the digitization of experimentation has opened up a really rich landscape that I think gives us a number of different knobs and levers we can use to understand the impact of policies we suggest on queuing systems. And I would say that the applied probability community is uniquely poised to contribute to this area. Given this, I think, combination of mathematical modeling along with statistical guarantees that's needed. And I don't really think that so far we've seen that interplay emerge as a kind of important and foundational area, either for the queuing community or within the community that works on experimental design in this space. So that's something that I'm hoping this talk can inspire some of you to take up the mantle on and push forward. So let me stop there, and I'll turn it back to Carrie.
Thank you very much, Ramesh. That was excellent. It's exciting to see that intersection of the different areas. And I mean, my background is in statistics, and so we have some work here in our group on sort of Bayesian adaptive experimental design, and so I'd like to talk to you about that at some point too. That would be really interesting.
Great, that's super
and there's
interesting.
a lot of connections to what you were talking about there that would be very interesting to pursue.
I feel bad that I didn't mention Bayesian methods at all. The talk was already overwrought as it was, but I think I'm glad that you brought that up.
Yeah, no, it's very interesting, and I understand that there's I know that there is a Q&A session, a discussion session after this session, so from 12 till 1. The link should have been sent to the participants, and it's also appeared in the chat or in the Q&A. So I invite everybody to join that new link at 12, just when we finish now, and then can continue the discussion with the speakers. I'm guessing there's quite a lot that I'd like to talk to you about. So perhaps, given time, we will wrap up. And I realise that otherwise we might get kicked off this call anyway, given the time. So so thank you very much again, Ramesh. And I think that there's. Are there any other questions in the?
Do you think I can maybe just provide
there
two?
is. Okay, so
maybe I could just provide two one-sentence responses to Shane and Nikki.
Just Nikki, maybe summarize the question and then yeah, provide the response. That'd be great. Thank you.
Absolutely, yeah. So Shane asks essentially about what happens if the state space is infinite, and he also essentially answers his own question, where he says, "Would I have to do some state space truncation, discretization, or other tricks?" The answer is yes, yes, and yes. And there would be some bias then introduced because of that. Although I'm not sure how much to obsess about that, because, like I said, the non-parametric approach is already sort of impractical, and even applying in a finite state space setting in reality, you'd probably still want to do some state aggregation. So I think that's a very fair point, Shane. And that's kind of what I think makes the applied modeling side of this interesting. You're trading off one bias for another, and it's not at all obvious how these interact with each other. So that's, I think that's a very perceptive and very interesting question. And then Nikki asks, there's potential for learning across states. Can I build other types of look-ahead information, combining approaches with predictive modeling or using prior beliefs? Actually, it's great you brought that up, because that connects to Carrie's comment about Bayesian methods. I think it is absolutely the case that one could think about sort of richer models of information gain across time, which sort of makes sense because I had to skip over it, but at the end of the day, it really is a particular type of reinforcement learning problem. So I think where your question is going, Nikki, is almost like asking, if we think of this as an RL problem, what happens if we apply methods from that space to thinking about experimental design? And I think really, if I was going to do that, I would encourage moving into a more concrete application, because that's where I think some of the state aggregation issues that Shane brought up as well, one would want to take those seriously, because at the end of the day, the goal then is to get to a practical, implementable experimental design. And I think that, that's where pulling ideas from RL, pulling some of these ideas of state aggregation would actually be a little more beneficial once you're working within a concrete applied context. So that's also some of the things we're trying to do as well on our side. So yeah, I'll stop there on the dot and let you move over to the other session.